Hey guys, it's Sunday and usually it means a study day for me. In this video, I will be quickly introducing the way I'm going to approach this video series and also start working on the first set of problems. My linear algebra course has started a week ago, so it's been a week of classes and the pace is picking up really quickly. There is no slack time. I have lectures every single day plus 3 tutorials per week. This class will be going for 7 weeks, and all the material will also be packed into those 7 weeks since this is a summer course. This is also a challenging course for many, including myself, since this is more abstract and proof-based. Therefore, I definitely need to learn how to write proofs, and the sooner I learn to do it, the better. The following topics were covered in class in week 1. Vector spaces, subspaces, span and spanning sets, null space, kernel, linear independence/dependence. But the tutorials this week were all concentrating on solving the problems from the first linear algebra course we took last year, so we can use those concepts more confidently and effectively in this course, because really there is no wiggle room. If you want to do well in this course, you better know your definitions of the main topics and know the connections between them. And this is where I'm going to start my linear algebra series from the quick review of the topics we need to get through before we can work on the problem sets in the course for the linear algebra 2. The way I will be structuring this video, I will be first introducing a topic, all key concepts and ideas we need to know, and then follow up with some example problems that I will take from our suggested exercises list given by our professor. The textbook we're using in class is called Elementary Linear Algebra by Anton and Rorres. I believe it's 11th edition. So I will link it down below, the physical copy and also a free PDF version of this, as well as some other textbooks, or at least one, which I like to use. I started reading it 2 weeks ago. It's Linear Algebra Done Wrong by Sergey Trail. I really like it, even though it's a bit more advanced, I would say. But nonetheless, it's very insightful to read the same topic from the other angle and explained by somebody else. The way I intend to film these videos is in a way that I will try to explain the topics and my thought process to myself in the first place. And if you guys find this helpful, then it's even better, because we are all learning. It's a learning curve for me, just as it might be for you if you're watching this video. So enough talking and let's get to work. Okay guys, the way I'm going to be approaching solving the review problems is by starting with the problem, seeing what the problem wants us to do, and identifying any key terminology that I don't understand or I don't exactly remember how to do it or what that means. So I will go back to the textbook or any source you like if you're doing it yourself, and I'll remind myself of the concepts, topics, and write down anything that is really important. So I've done that for this video up front, so it doesn't take so much time. So basically, here's the problem we will be working on today, or at least in this episode. It states that suppose we have two vectors u and v, both are non-zero, non-parallel, and they are in 3D space. And let these two scalars k and l be defined like this, and we need to prove that some other vector w, made up of the product of the other two, u and v, bisects the angle between u and v. So the first thing to note here is that, well, bisects means that this vector basically splits the angle between u and v in half. Okay, so that's the first step. Then anything else that might come handy in this type of problem is, so it will be good to know what the norm means, norm of a vector, and along with it follows the dot product and some other useful things. So here's what I've written out here. So basically I have a definition of a norm, which is defined in any dimensional space like Rn, but in our problem we have R3. So we will have only 3 components in this formula here. Then we move on to a theorem that states some properties of the norm. And one of the properties that we will be using by solving this problem is this one, where the norm of a product of a vector and a scalar can be rewritten like this. You can pull the scalar out with the absolute sign in front. Another definition is the definition of the dot product and the formula to connect it to the angles between the 2 vectors and these 2 relationships here. So the norm of a product, the norm of a vector is the same as the square root of vector times vector, and the triangle inequality. So all of these things that I have written out here, I have used to solve this problem. It seems like a lot of things to know, and if I look at this, if I continue doing it in this way, every single problem I have on my worksheet, and I have 12 of them, deals with some other combination of topics and ideas from the first linear algebra course, and by going through every problem, I suppose we will be reviewing the most of the material from that first course. So it might seem like a lot of work at first, but it's going to save us a lot of time later. So let's move on to solving this problem. The way I intend to approach it is that I assume that vectors u and v, let's say they are like this. And then there's a vector w that splits the angle between u and v in half. So I'm going to show that this vector and this vector, not the vector, I'm sorry, this angle and this angle are exactly the same. I will call this angle to be theta, and these ones will be then theta over 2, according to our problem. Okay, so now from our handy cheat sheet here, we know that cosine theta equals the dot product of u and v over the product of the norms of these 2 vectors. Oh, sorry, didn't see anything. Okay. Well, next step, so I'm writing out here one more time the facts from the problem. So we have vector w given as L times vector u plus k times vector v, and we also know that L equals the norm of v and k equals the norm of u. Okay, so I'm gonna try and write it out somewhat like a proof. The first thing to do when you write a proof is to define your variables. So here we have vectors u and v and w. And let theta be a vector between u and v. Let the angle between u and w be denoted as theta over 2. The same thing we will write for vector v and w. Okay. So now we can start solving some problems here. Okay, so we know that vector w is defined like this here. And so let's write it out. Okay, now we're dealing here with the norm of a sum. If we look at our cheat sheet here, we can rewrite the norm of a sum as the sum of the norms. And at the same time, we can also go ahead and multiply the brackets on the top. Okay, so I'm just gonna go step by step because there is another step here that can be done right away. But just for the sake of showing you, I'm gonna write it out. This bracket here can be also rewritten in another way. We can deal with the scalar and the vector and the norm of the product of these two. We can just pull out the scalars out of the norm based on that rule here. Oh, and we can also use this fact to simplify the numerator a little bit. Let's use the fact that K and L are actually these here. Okay. And replace all the norms with K and L and see what we get. Now what we can do here, we can cancel 1K from each. Oh, no, wait, this can be combined before we do that. So now we can cancel some K's here. This goes, this goes, this goes. And so we have L times K plus U times V over to LK. So this is our answer. This is what we've got for the angle theta over 2 between U and W. Now we go from another side. Now let's see. But this time we go with vectors V and W. Yeah, sorry guys for all the messy writing. This is my first video of this type, and I tried to film it and refilm it and write and rewrite, so I still have to learn how to do it properly. But nonetheless, this is it for today, and that was the problem of the day, and I'll see you in the next clip.